Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 42. Today we will talk about op-amps. Op-amps are an interesting and important component in electronic design. And we will see examples of circuits that use op-amps in them to build interesting functions. So today we will begin by looking at some op-amp basics. You might have seen op-amps as a black box in circuit theory courses, etc. But we'll start from scratch and assume you have no knowledge of them. And then we'll look at a couple of amplifier topologies that use op-amps in them. It's strange that we have amplifiers within amplifiers, but they have some interesting properties that we will explore. All right, now before we go there, the interesting question here is, what do we mean by operational amplifiers? Are there amplifiers that are not operational? What does operational mean? Does it mean just works? Is that why we call it operational? And the answer goes back to 1940s when people were using amplifiers of this nature to simulate or emulate more complex systems. All right, so here's a problem that we faced. This is an airplane flying in the sky, and this airplane experiences various forces. We have the gravity, etc., wind, and the engine force, and so on. And we want to analyze the stability of this airplane. Will the airplane shake or not shake? Will it crash, not crash? All these things. This was a real problem back then, back in 1940s or earlier, when they were building either commercial airplanes or military airplanes. And the problem was that at that time, there were no calculators, no computers, nothing to be able to simulate this structure and see whether it's stable or not. What we did know was we could write a bunch of equations for it. The equations were of this sort. We won't go through them. And they were just differential equations, as you can see by these various partial derivatives. So we had a relatively complex differential equation that we had to solve. And the thing is that we had some flexibility. You have the mass of the structure and various other forces. So some of those have numerical values, some of them don't. And the question is, how do we choose these different parameters of the airplane to make it stable? So back then, people came up with a concept that maybe we can try to simulate this differential equation, these equations with all these partial derivatives in them. And the way we are thinking is that every differential equation consists of some differentiation operations, some integration operations, and some summation operations. Right? That's more or less what we have. So if we could build some circuits that can perform differentiation, integration, and summation, maybe we can use those circuits to simulate what this airplane will do. If that circuit has a stable behavior, then maybe this airplane will also be stable. So for example, in this paper back in 1947, Razavi shows all these circuits that are based on op-amps. So this is an op-amp, and it says you can connect some devices around it. In fact, we will see some examples of that today. You have different types of devices connected to these op-amps, and they perform different types of functions. And he proposes this for called an electronic computer for symmetric motions of airplane. So this is what we call an analog computer because there are no digital quantities here. And back then, these were very popular to analyze mechanical systems, other systems that would otherwise be difficult to simulate. Interestingly, Razavi also proposes the phrase operational amplifier. You can see here it says, as an amplifier so connected can perform the mathematical operations of arithmetic and calculus on the voltages applied to its input, it is hereafter termed an operational amplifier. So the term operational means an amplifier that simulates an operation. a mathematical operation, differentiation, integration, etc. That's where the term comes from. Okay, so our objective is to understand some of these circuits. Not that we're going to try to simulate airplanes, but rather because many of these circuits are still important in electronic design. Now, first, we want to see what an op-amp is. Well, an op-amp is an amplifier. So we would expect that if you give it an input, it amplifies the input and produces it at the output. But what's interesting about an op-amp is that it has two inputs. That's a little strange compared to all the amplifier stages that we have studied in this course. We learned common emitter and common source stages, common base and common gate stages, and so on. And they all had only one input and one output. But now we have a circuit that has two inputs. Now, where do we learn how to build a circuit that has two inputs? Well, that will be in the next electronics series, not in this course. Those are what we call differential amplifiers. But for now, we just take it as a black box that has two inputs and one output. And we'd like to build circuits that would be useful using this black box. All right, so the op-amp is a black box for us for now. And it has two inputs. But why? Why do we need two inputs anyway? All right, so here's what it is. We have a black box. It has two inputs, which we call V in 1 and V in 2. And these two are different inputs. And that's why we have a positive sign here, a negative sign here, to distinguish them from each other. And then here, we have an output. This output is with respect to ground. So we might write it like this. Or, as usual, maybe not even show this and just place V out here. Either way is fine. Okay, so this is the structure, the symbol of an op-amp. Now, we have two inputs. That is a little strange. Well, the way this op-amp works is as follows. If we set one input to 0, let me change these just to make it a little easier. I'll call this V in 1 and this V in 2. It's more natural to do it that way. So V in 1 and V in 2. If we set this to 0 and we give it V in 1, the amplifier amplifies V in 1, gives us an output. If we set this to 0, the amplifier amplifies V in 2 and gives us an output. There's only one difference between these two experiments. In one experiment, with V in 1, the gain is positive. For example, the output is 100 times the input. In the other experiment, the gain is negative. For example, the output is minus 100 times the input. So that's the only difference between these two inputs. So now it makes sense to call these inputs names to make sure that we always remember they are different, right? So we'll change the color and we'll call this one, which goes to positive, the non-inverting input. So this arrow should actually point to here. And then this input of the op-amp is called inverting input. So we do need to distinguish between these two. Okay. Now, in the back of your mind, you might be asking not only how do we build inside here a circuit that has two inputs. We haven't seen that. And as I said, that's for the next course. But also another question. Why do we need an amplifier with two inputs? It seems that the amplifiers we had before, the common source stage and the common emitter stage, etc., will suffice. So why do we need to have an amplifier with two inputs? Okay, so the answer to this question is as follows. There are two advantages. Number one, if we have two inputs, we can build certain circuits that would not be possible to build with only one input. And I will show you at least one example today. And the other is that sometimes if we have a complex circuit consisting of lots of transistors and stages, etc., if we, in our mind, we can simplify that, or we can view that as an op-amp, then that circuit becomes easier to analyze. So these are the two advantages of having this op-amp picture in mind. Okay, so we have two inputs and one output. We have an amplifier, so there must be some sort of voltage gain involved. We call the voltage gain A0. And what this means is that V out is equal to A0 times V in 1 if V in 2 is 0. Right? Just a simple amplifier with a positive gain. Or V out is equal to minus A0 times V in 2 if V in 1 is 0. Very simple inverting amplifier, like a common source stage. But the question is, if I apply both V in 1 and V in 2 at the same time, what do I get for V out? And the op-amp behaves as follows. It says, I will subtract V in 2 from V in 1. I will multiply the result by A0, and that's what I will produce at the output. That's the job of the op-amp. So the op-amp will produce at the output the difference between the inverting input voltage, the non-inverting input voltage and the inverting input voltage, and we'll multiply it by A0. That is what the op-amp does. Okay, this equation is important to remember. All right, so with that, we can see, we can take a quick look at the characteristics of the op-amp. So let's look at the input, output characteristics. We're just trying to ease into this domain and understand what this all means. So here's the way we are thinking. Let's construct the following setup. I take the op-amp, I set V in 2 to 0, I apply a variable voltage to V in 1, and I measure V out as V in 1 varies. V in 1 varies from minus infinity to plus infinity, and I would like to measure V out. Well, that's a very simple amplifier. So if I plot V out as a function of V in 1, I have a straight line. Hopefully, if it's a good amplifier, this should be a straight line. And what we know is that because V out in this case is A0 times V in 1, the slope of this line is A0. So that's what we have for this measurement. Okay, now let's switch the two inputs. So in the next experiment, we apply an input to the inverting input. We call that V in 2. And we set the other input to 0. And again, we measure V out as a function of V in 2. So what do we get? So here's V in 2 going from minus infinity to plus infinity. And here's V out. And what we see is that if V in 1 is 0, V out is equal to minus A0 times V in 2. So it's a straight line, but it has a negative slope. So it goes like this, and the slope is minus A0. Okay, it's a pretty simple concept. All right, so based on these, now we can go ahead and define what we mean by an ideal op-amp. If you could have an ideal op-amp, what characteristics would you look for? So I will write ideal op-amp here. And I would like to have a very high gain. So A0 would be infinite, right? So we say A0 should be infinite if we could build an ideal op-amp. Okay, what else? Well, we could also say that the input impedance of the op-amp, meaning going here, should be infinity, meaning that these terminals draw no current. For example, they could be gates of MOSFETs, right? If you have a gate of a MOSFET, here we have a very high input impedance, at least at low frequencies. So we say input impedance is infinity. How about the output impedance? The output impedance, well, ideally 0. We would like to generate a voltage, so this should look like a voltage source. A voltage source has 0 output impedance. That's the best type of voltage amplifier you can build. Okay, what else? Well, how about speed? This op-amp must be infinitely fast. So the speed, the bandwidth, for example, would be infinite. So bandwidth is equal to infinity. And power dissipation? Power dissipation should be 0, ideally, right? 0. Cost should be 0. Okay, so that's the ideal op-amp. Now, let's go and find an op-amp that we can buy standalone and off-the-shelf op-amp. For example, the 741. That's a very well-known and easy-to-use op-amp. So 741 is an op-amp that you can buy, and it's been around for, I don't know, 50 years, so it's a very versatile component. Okay, so the gain of this op-amp when you buy it is about 100,000. That's a very high gain. So 100,000. The input impedance is several mega ohms, so we'll just say several mega ohms. The output impedance is less than 100 ohms, so less than 100 ohms. The bandwidth of that op-amp is a few megahertz, 1.5 megahertz. So 1.5 megahertz. So not quite infinity, right? It's a low bandwidth op-amp. The power dissipation is about 80 milliwatts. And the cost is less than $1. I don't know how much it is, maybe $1 or 50 cents or something in that range. Okay, so when we compare these two columns, we see that the 741 approaches the ideal op-amp in a couple of respects, in terms of the gain and in terms of the input impedance, maybe even in terms of the output impedance, depending on what we're trying to do. But these other ones, of course, the cost is also relatively low, but these other ones are not really ideal. All right, but today, in most integrated systems, integrated circuits, we also have op-amps. And those op-amps are very different from the 741. So I will call this a modern integrated op-amp. So these are not op-amps that you could buy. They are not standalone op-amps. These are op-amps used inside the bigger systems. For example, inside a filter that you might have in your cell phone as you process the voice and data, etc. So for those op-amps, we have quite different characteristics. The gain is nowhere near this. So the gain these days is somewhere between 50 to 100, or even lower. The input impedance is still pretty high, so several mega ohms. The output impedance is higher, perhaps kilo ohms, several kilo ohms. The bandwidth is substantially higher. Bandwidth is several gigahertz. And the power dissipation, maybe 5 to 10 milliwatts. And the cost is extremely low. The cost is more like 10 to the minus 4 or 5 Okay, maybe even 10 to the minus 5. So maybe 10 to the minus 5. Because you could have many of these op-amps on one chip, and that one chip will sell for a low price. So what we see is that in modern integrated op-amps, we have sacrificed certain aspects of the ideal op-amp, right? We don't have a low output impedance. We don't have a very high gain, which we usually attribute to op-amps. But we have a very large bandwidth. It's a very fast op-amp. The price is extremely low. The power consumption is quite low. So these are the things that we strive for in such systems. All right. So let's go ahead and make a couple of observations based on what we have learned so far that are important in our circuit analyses. So, observations. So generally we are saying that the gain of an op-amp is high. Now high has different definitions. It could be 100,000 or it could be 50. It just depends on the application, the environment, etc. But let's just stay with that definition of high and see what we have. Well, if the gain of this op-amp is very large, but the output voltage swing is not very large, so let's say the gain of this op-amp is 100 or 1,000, but the output voltage here is only a few volts, as you would expect in reality. Then what we can say is, if this is a few volts, and this is, let's say, 1,000, then this is a few millivolts. So, observation number one, if V out is a few volts, and A0 is on the order of 1,000, then V in 1 minus V in 2 is a few millivolts. This is an important observation because it simplifies how we look at a circuit containing an op-amp and how we can quickly analyze it without writing too many equations, at least approximately. So this says that if I see an op-amp in a circuit, and I know in reality that the output swing here is not very large, after all, your power supply might be 1 or 2 volts or 3 volts, right? So the output swing is some amount, a few volts, and I know that the gain of this op-amp, let's say, is 1,000, then I can safely assume that V in 1 minus V in 2 is on the order of a few millivolts. In other words, V in 1 minus V in 2 is quite small. Okay? So V in 1 minus V in 2 is quite small. So anytime you don't remember why this is true, you just go back to this equation and remember that we're assuming this is not very large, as is the case in practice, and this is quite large, so this has to be very small. That's the rule that we always remember about an op-amp and the difference between its inputs. Okay, so remember that. Very well. The next observation that we will make is the following. So if we can visualize a complex circuit as an op-amp, the analysis becomes simpler. So I'll give you an example. Let's say you go for a job interview and the person says, here's a circuit, tell me, for example, how much gain it has. So here's the circuit that the person draws. The interviewer says, I have 3 common source stages, one after another. So it's a cascade of 3 common source stages. Okay? Now we know how to do that. That's easy. This gain times that gain. But what the interviewer is showing you is like this. We have a resistor from here to here, and then we have a resistor from here to here. This is R1, this is R2, V in here, and V out here. And the interviewer says, can you give me an estimate for V out over V in, the gain from here to here? The small signal gain. And I look at that and say, oh my God, well, I know how to analyze these 3 stages, but I don't know what to do with these resistors going back. Do I have to write KVLs and KCLs, etc.? All right? Okay, but now, if you identify the cascade of the stages as an op-amp, so you say, well, you know, this whole thing looks like an op-amp. So I will redraw this like so. I will redraw this like so. R1, R2, V out, and V in. Then maybe I can say something about that, right? This is a familiar op-amp topology. Now, of course, the complication is that here looks like we have only 1 input, but we would like our op-amp to have 2 inputs. How do we reconcile these 2? Well, that's easy. What really happens is that this circuit has actually 1 input here, 1 input here. One is grounded, right? So you can say that the other input is grounded. After all, this gate voltage is measured with respect to ground. So I can just assume there's a ground here and say, well, this is just a simple op-amp based amplifier, and I can quickly answer the question. So it is this abstraction of going from a complex circuit to a familiar topology that is extremely valuable in analyzing circuits or even designing circuits. So it's not just that we want to use op-amps as a building block, it's also that sometimes we want to view things as op-amps for a better understanding of the operation. Okay, in the next step, we would like to look at some amplifiers that use op-amps in them. Now it's strange because op-amps are amplifiers themselves, but we will build amplifiers that use op-amps inside, and we'll have to see why that's a good idea. So let's go ahead and add another page here. Okay, so we'll look at what we call non-inverting amplifier. This is a type of amplifier that uses an op-amp as a black box. Okay, the topology is very simple. You probably saw this in basic circuit theory courses. We start out with an op-amp. And we take the output voltage and divide it down using a resistive divider. So here's a resistive divider going to ground R1, R2. So we see that here we have a divided version of V out. We can easily calculate that if we really want to. It would be R2 over R1 plus R2 times V out. And then we feed this divided voltage to this input of the op-amp. And this is extremely important. What goes back here has to always go to the inverting input of the op-amp. Okay? If you swap these two in the lab or in your simulations, the circuit will go crazy. So we cannot do that. In this type of feedback, in this type of amplifier, what we're bringing back is called feedback. What we are bringing back has to go to the inverting input of the op-amp. All right? Okay, and the input is right here. This is called a non-inverting amplifier, and we will see soon why it is called such. Okay, so we would like to analyze the circuit. And as usual, we start with a simple view. What if the op-amp is really ideal? Meaning it has a very high gain. Then can we predict the gain from here to here quickly? Let's try to do that. So case number 1, A0 is approximately infinity, this A0. Okay, so if A0 is very high, I can say that from the previous page, if I call this V in 1 and V in 2, what I do remember is that this op-amp always behaves as this. V out is always equal to V in 1 minus V in 2 times A0. Right? That's what the op-amp does. Regardless of what we put around it, that's what it wants to do. Now, if A0 is very high and V out is not, we're using this in a reasonable application with some moderate voltage swings. So this is finite. This is very large. So what we get is that this has to be very small. Okay? So if it's so small, I can say that V in 1 and V in 2 are approximately equal. So that means V in 1 is approximately equal to V in 2. All right, so I hope you understand this line of thought here. We start out by remembering that that's what the op-amp does, and observing that in reality, the output voltage swing of an op-amp is not very large. It's only a few volts. So if the gain of the op-amp is very high, then V in 1 minus V in 2 must be small, which means V in 1 and V in 2 must be close to each other. Okay, so then this voltage is approximately equal to that voltage, right? And this voltage is just the same voltage as here. It's just a piece of wire. So I can say that this voltage here, which is V in 2, is approximately equal to V in 1. And V in 1, it just happens to be V in, the main input that we have applied to the circuit. So we say this is approximately equal to V in. I hope these are not confusing. V in 1 and V in 2 refer to the op-amp itself. It has one input here, one input here. They have names, V in 1, V in 2, or non-inverting input and inverting input. V in is what's coming from outside to this whole circuit, to this whole amplifier. And we observe that these two are close to each other, and this is called V in, therefore this should be close to V in. All right, so now, given this voltage, I should be able to find this voltage. It's easy, right? If the voltage at this point with respect to ground is approximately equal to V in, then this current is known. That current is V in over R2. And that current is multiplied by R1 to generate this voltage, or you can multiply it by R1 plus R2 to generate this whole voltage, right? So we can say V out is equal to this current, V in over R2, times this entire resistance, R1 plus R2. We can write this because we are assuming that no current flows this way. Right? All the current from R1 ends up in R2. So that goes back to the assumption that the input impedance of the op-amp is very high. If it weren't that the case, we couldn't write this equation. Okay, so we have a V out over V in is equal to, if we divide this, we get 1 plus R1 over R2. And this is the voltage gain of this overall amplifier topology from here to here. So this has many interesting design consequences for us. It has some advantages over simple amplifiers that we learned to build before. For example, if I have a common source or common emitter amplifier, so here's a common emitter amplifier, We have RC here. And we know that the gain of this guy is given by minus GM RC if we neglect early effect. So we are not happy with this voltage gain, and that's why we go to this amplifier topology. The reason being, if you remember, this has dependencies upon many things. It depends on process and temperature and supply voltage. Whereas here, you see the beauty of this result. It doesn't even depend on A0. Even if A0 is not infinite, it's large enough, it doesn't depend on that. It just depends on R1 over R2. And in integrated circuits, we can create this ratio with very high accuracy. If, for example, temperature goes up, R1 goes up and R2 goes up together. So the ratio remains constant. Or if we go from one wafer to another wafer, even though the value of R1 goes up from this wafer to that wafer, the value of R2 also goes up, so that the ratio is always the same. In fact, when we want to build this structure here in an integrated circuit, this is how we would do it. We start out with a structure for the resistor. If you look from top to the wafer, the resistor looks like this. It's a rectangle. There's a contact here, there's a contact here, and we have the resistance between these two. Okay, this material itself is resistive, so by putting two wires here, we have some resistance between here and here. Very simple. We're just looking from top of the wafer. So let's say this is R2. And I would like to have a gain of, for example, 3. So the gain has to be 3, which means R1 over R2 has to be 2. So I would like R1 to be twice R2. All right, so this is how I do it. I will draw this twice over here. The same exact geometry. I copy this geometry here and here. And then I connect these two together. And I call this R1. So R1 is exactly twice R2 because it's the same structure that's copied over here. And if this value goes up and down, these all go up and down together. So the ratio is very well controlled, and this overall gain is very precise. And that's the beauty of this amplifier as opposed to the type of amplifier that we have studied in the past. So this amplifier has many applications where this gain has to be very precise. If you want to have a gain of, for example, 4.00, then you cannot use this. You have to use this. All right, so this is the case of very high gain. Now in reality, you say, well, no, actually my gain is only 50. I said that in some modern op-amps, the gain can be as low as 50 or even lower. So then, this is not exactly correct. Let's go ahead and find a more accurate expression when the gain of the op-amp is not very high. So we go to case 2, and we say A0 not very high. Okay, so from an engineer's perspective, what we do is anytime we see a circuit like this, our first reaction is to assume A0 is very high and quickly come up with this in our mind. But now we say, well, how much gain do we really need here? 10,000, 100,000, 1 million, what? And for that, we have to understand how the finite gain of this op-amp affects this overall performance. So we have to go through this analysis. Okay, so I would like to analyze the circuit again, but this time assuming A0 is not very large. If A0 is not very large, I cannot assume that V in 1 minus V in 2 is very small, which means I cannot assume that V in 1 is equal to V in 2, or this is approximately equal to V in. So I have to start from scratch and analyze the circuit without any of that knowledge. All right, well, what we do know, regardless of what's going on, is that this is a resistive divider. So this voltage is always equal to V out times R2 over R1 plus R2. So we say, I will call this node X. So we say, regardless of what's going on, Vx is always equal to Vout times R2 over R1 plus R2. So that we know. All right, we also know that this op-amp always performs this function, regardless of how much A0 is, etc. Right? This op-amp says, I will subtract this value from this value and multiply the result by A0. So let's go ahead and do that. The op-amp says, I will subtract this value from this value. So we write V in minus this value. How much is this value? This is Vx, what we just found. So Vout times R2 over R1 plus R2. The op-amp takes the difference between these, multiplies it by A0, and generates the output, Vout. So now we have one equation in terms of Vout and Vin. We can find Vout over Vin. So Vout over Vin is equal to, so if we write it out, we get A0 over 1 plus R2 over R1 plus R2 times A0. This is the general equation for the gain if A0 is not infinite. Just to check, let's set A0 to infinity and see if this equation reduces to this equation. All right? So, if A0 goes to infinity, this becomes dominant, this crosses with this. We have R1 plus R2 over R2. So we have 1 plus R1 over R2. 1 plus R1 over R2, we're good. Okay, so this is the general equation. This equation also tells us something interesting. It says, for this equation to hold, we don't need A0 to be infinity. All we need is for this term in the denominator to be much greater than this term. Right? So that's the condition that will give us this approximation. So that's good to remember. We need R2 over R1 plus R2 times A0 to be much greater than 1 so that we can use this approximation. As I said before, this approximation is very desirable because the gain of the overall amplifier is independent of everything else, independent of A0. Here we have some dependence on A0. If we make sure that this term is much greater than 1, then we don't have much dependence on A0. So if R2 over R1 plus R2 times A0 is much greater than 1, then Vout over Vin relatively independent of A0. Okay, so it's just given by the ratio of two resistors. It's very precise. We can have high precision gain for this type of amplifier. All right, now when we are playing with these types of equations, especially this equation here, there could be a bit of confusion. We have two types of amplifiers here. We have the op-amp itself with the gain of A0, and then we have this whole monster with the gain of Vout over Vin equal to this expression. So anytime I say the gain, which gain am I referring to? And to make sure that we don't confuse these two gains, we will give them some names. So here's the way we call these. So let's go change the color to maybe brown. Okay, so A0 will be called the open loop gain. Open loop gain means when this op-amp is by itself, is not connected to anything else, you just bought it from an electronic store, it has a certain gain, like 741 has a gain of 100,000. And then this overall gain is called the closed loop gain, meaning this whole expression here. Closed loop gain because we close the loop around this amplifier. This is what we call a feedback loop, and it's something that we will study in the course after this course. All right, so the open loop gain is just the gain of the op amp. The closed loop gain is the gain of this overall amplifier. All right, let's give you a quiz just to see if you're up to speed. Here's a little circuit that I have cooked up for you. Negative here, positive here. And let me draw this more carefully. So, so you go for a job interview, and they give you a circuit like this. And they say, assume A0 is very high. All right? And we would like you to find the gain from V in to V out. So V out over V in, how much is the voltage gain? I'll give you 90 seconds to think about it. You can assume channel length modulation is negligible. So lambda is 0. All right, so what answer did you get for the gain? This is what we call the closed loop gain. Well, we go back to the same principle. We know that the op amp always enforces this equation, and if A0 is very large, then V in 1 and V in 2 must be very close to each other. So this and this are very close to each other, meaning that if this is called V in, this is approximately equal to V in. So we say this is approximately equal to V in. But this voltage, this AC voltage, is produced by this common source stage. So, because we know the gain of the common source stage, we should be able to find the input signal to the common source stage. If the output signal of the common source stage is V in, the input signal is just V in divided by the gain of the common source stage. So this voltage here, the AC signal here, is approximately equal to V in over minus GM times RD. All right. Okay. So, and now we see that this voltage goes and gets connected here. We see that this V out is the same as this voltage, right? So we can say that V out is equal to minus V in over GMRD, and that means that V out over V in is equal to minus 1 over GMRD. All right? So that's a little circuit that we have, not necessarily very useful, but it exercises our knowledge of these things. Another way of thinking about it is that you could have started from here. We could have said, this is V out. So we have V out here. This must be minus GMRD times V out. So minus GMRD times V out is here. And we know that these two are equal, so we have to have minus GMRD V out is equal to V in. Minus GMRD V out is equal to V in, so that's what we get. All right, as you might have noticed, I have connected this to the non-inverting input of the op-amp because I want this whole loop from here to here to contain one inversion. The inversion is already provided by this, so this should go to positive, not negative. Okay, we can now go on to another type of amplifier that also uses op-amps, and this amplifier is called the inverting amplifier. It's a little different from this one. It still uses an op-amp and two resistors. Okay, so in the inverting amplifier, we have an op-amp with two inputs. This time we draw the inverting input on top. Doesn't have to be, but just for simplicity. And we ground the non-inverting input. So that's a clear distinction between this amplifier and this amplifier. Here, neither of the inputs was grounded or close to ground. This goes up and down, this goes up and down, the output goes up and down. But here we have that. So, and then we apply a voltage at the input through a resistor, call that R1, and then another one here, call that R2, and this is the output. By the way, we call this a non-inverting amplifier because the gain is positive, right? It doesn't invert. So as you might expect, this is called an inverting amplifier because V out over V in is negative. So the overall circuit inverts the signal. But we'll get there shortly. Okay, so as usual, we'll analyze this in two cases. First, we assume the gain of the op-amp is very large, just to get a quick glance at the operation of the circuit. And then we assume A0 is not very large and quantify it more carefully. All right, so case number one, A0 is very large. Okay, so going back to this fundamental equation, which always holds as long as the op-amp is healthy, we know that if A0 is large, V in 1 and V in 2, these two have to be close to each other. Now in this case, we have something interesting going on. One of these inputs is 0, is exactly 0. So the other one has to be close to 0. You can see that the larger A0 is, the smaller the difference. So the larger A0 is, the smaller the difference, meaning that this will be closer and closer to 0. So if I call this node X, we call node X, which is close to 0, a virtual ground. It's not exactly ground, because this voltage is not exactly 0, but it's very close to 0. So we call this a virtual ground. And this is simply a property that arises from this fundamental operation of the op-amp. Okay? This holds regardless of what the op-amp is doing or what configuration it's in. This is a relationship between the output and the input. Notice that we have a virtual ground here, but we do not have a virtual ground here because neither this nor this is close to 0 or at 0. Okay, so a common mistake is for people to think that a virtual ground is 0 and then try to ground this, connect this to ground, and that messes up everything. So don't do that. Remember that if A0 is 100,000, 1 million, etc., this difference becomes smaller and smaller. But this is not a ground point. It's a virtual ground point. Okay, So let's find the voltage gain V out over V in this case. If X is very, very close to 0, then I can say that the current through R1, which is equal to V in minus Vx over R1. So current through R1 is equal to V in minus Vx over R1. This voltage minus this voltage over this resistance is approximately equal to V in over R1 because Vx is so close to 0. All right. So that's the current going this way. Now this current comes through the resistor, reaches that point. Now it cannot go this way because we have assumed that the input impedance of the op-amp is very high. It draws very little current. So the current coming from R1 has to go this way through R2 and go to the output of the op-amp. So the current through R2 is given by the same expression. If I multiply the current through R2 by R2, I find the voltage drop across R2. So let's do that. Let's multiply V in over R1 times R2. This is a voltage that is sustained across R2, with its positive on this side and its negative on this side. Okay, all right. So that voltage should be equal to this voltage minus this voltage, right? That's what we said. This voltage minus this voltage over this resistance is the current. So that should be equal to Vx minus V out. Vx is close to 0, so let's not worry about that. So we see V in over R1 times R2 is approximately equal to minus V out. So that says that V out over V in is equal to approximately minus R2 over R1. And that is the approximate voltage gain of the inverting amplifier. You can see that there's a negative sign, so it's called inverting amplifier. And that's in contrast to what we had here. So one difference is the inversion, and the other one is that this has a 1. This one does not have a 1. All right? Okay, but we see similar properties. Again, R2 over R1 is a very well-controlled quantity. We can use resistors like these structures on an integrated circuit to make sure that we have a high precision value for the closed loop gain of this amplifier. All right, even though the open loop gain, the gain of this op-amp may not be very precisely controlled. Okay, so that's what we call an inverting amplifier. And the choice between this guy and this guy depends on a number of parameters, one of which is the input impedance. The input impedance here is quite high. We're going to an op-amp. This input of the op-amp doesn't draw much current. So there's a very high input impedance. Here, the input impedance is not very high. How much is it anyway? We can quickly find that, right? How do we find the input impedance? We kill all the independent sources in the circuit. We apply a voltage from outside and measure the current. So let me do that on this side, just so you see how this is done. So remember how we did this? We applied a little voltage source here, Vx, and measured this current, Ix, right? Well, small signal really, Vx and Ix. Well, this setup is really the same as here. I just changed the name from V into Vx. Okay, if the gain of the op-amp is very high, we have a virtual ground here, which means this point has very little voltage on it. So the current through R1 is equal to this voltage minus this voltage over R1. This voltage close to 0, so it's just this voltage minus this voltage over R1. So the input impedance is approximately equal to R1. And that's what we observed before too. Remember we said current through R1 is this much? So that's obvious. So the input impedance in this case is approximately equal to R1, which may not be very high. In general, actually, it's not that high. So that's the difference between this topology and that topology. Sometimes we use this, sometimes we use this. All right. The next question, or the next case, is when this gain is not infinite, so A0 not very large. So just like the non-inverting amplifier, we assume the gain is not very large, and we would like to analyze it and see what we get. So let me go to this color here. All right, so if the gain is not very large, I cannot assume that this is close to 0. No problem, we'll just go ahead without that assumption. All right, let's call this Vx. If we have a voltage V out here, and we know how much, let's say we know how much it is, can I predict this voltage? Yes, because going back to the fundamental equation, we call this V out, we have the gain A0, we have V in 1 equal to 0, so we can find minus V in 2, which is Vx. So we have Vx is equal to V out over minus A0. So if we have a certain voltage at the output of the op-amp, we require this much voltage here. If A0 were infinite, we wouldn't require much voltage, but A0 is not, so we require this much voltage here. If you take this voltage and multiply it by minus A0, you get V out, right? So that's why this should be correct. All right, now we go ahead and write a KCL at the node X. So again, I'm not assuming node X is a virtual ground. I just use basic properties of the op-amp and a KCL. Okay, KCL at this point says V in this voltage minus this voltage over R1 is this current. This voltage is given. So plus V out over A0 over R1. That is the current flowing through R1 from left to right. This should be equal to the current flowing through R2 from left to right. So the current through R2 is equal to Vx minus V out over R2. Vx, we know. So minus V out over A0, that's Vx, minus V out. This is the total voltage across R2 divided by R2 gives us the current through R2 going from left to right. So this current comes in and it has to go through R2. Okay, so if we simplify this, for V out over V in, we obtain the following. So this is the closed loop gain when the open loop gain is not very large. So we get something like this, minus 1 over R1 over R2 plus 1 over A0, and then we have R1 plus R2 over R1. This is the overall voltage gain of the circuit if the gain of the op-amp is not infinite, is not very large. So again, we can see what's going on. We can see that if the second term in the denominator is much greater than the first term, then, much smaller than the first term, meaning if A0 is very large, if the second term is much smaller than the first term, then the equation reduces to R2 over R1 with a negative sign, and that's what we had before. So that makes sense. That also gives us the condition for this equation to hold. The condition is that we want this expression, the second term, to be much smaller, much less than the first term. All right? Okay. So this is what we obtain for this type of circuit. and this is called an inverting amplifier. Our time is up. Next time we will look at other circuits that use op amps to create interesting functions. I will see you next time.